Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to talk about why atomics were added to C++. Atomics. In our last video, we started discussing the memory model that was added to C++ 11. You can think of the model as rules or definitions, which were added to the core language. This provided the necessary tools so the standard library could be improved, which made a huge impact on multi-threaded applications. If you have not yet seen our C++ memory model video, we encourage you to take the time to watch it. In this video, we will continue on and talk about the impact atomics have in multi-threaded programs. We will start by explaining what problems atomics solve, when to use them, how to use them, and show a few examples.
There is no reason to use atomics in a single-threaded application. The purpose of atomics is to synchronize memory access to shared data between different threads, which are running simultaneously. If there is only one thread, there is no memory access conflict, so using atomics will just add overhead and provide no benefits. Even in multi-threaded programming, not every application benefits from using atomics. With multiple threads that share no data, there is nothing to synchronize. When shared data does exist, having each thread acquire a lock and wait its turn is often more clear and easier to reason about. You should only consider using atomics when the threads must work on the same data at the same time, and it is not acceptable to have a single thread stall out. In our example, we have a main thread and two worker threads. The main thread will create an atomic int and set its initial value to 0. Thread A and thread B are started at the same time. Thread A sets the value of the variable to 10 and then changes it to 20. Thread B reads the variable. Since threads A and B are running simultaneously, it is unpredictable how the memory reads and writes will be interleaved. Thread B may see the initial value of 0, the intermediate value of 10, or the final value of 20. These are all valid answers according to the memory model, and the behavior could vary from one run to the next. If this is not something your application can tolerate, there are some strategies you can add to your code. We will cover these in our examples. Let's start by going over the definition. An atomic is a templated data type. If you're not familiar with std atomic, the T is similar to the T you would find in std unique pointer or std vector. It stores a single value of type T, where the T is usually some primitive type like bool, int, char32t, or long. There is also a template partial specialization, which accepts any raw pointer, like widget star. There is nothing special about the data stored inside an std atomic. What is special are the instructions the compiler uses to read and write the data. Reading from an atomic int which has not been initialized is undefined behavior, just like reading from a regular uninitialized int. Starting with C++ 20, this initialization is not required, and the initial value will be 0. For readability and consistency, we strongly recommend initializing every primitive data type. All of the normal rules of implicit conversion between data types apply to atomics as well. If you declare an atomic integer and assign a floating point value, the fractional part of the data will of course be truncated. This is not a property of the atomic data type. This is simply how conversions work. Although an std atomic contains a single value of type T, there are restrictions placed on its usage. Atomic types are not copyable or movable. This means that creating a vector of atomic types is not allowed, since vector requires that its elements be movable. You can have an std unique pointer that points to an atomic type. However, you will not be able to move this unique pointer. There are also constraints on the T that is being stored in the atomic. The T itself must be copyable and movable, and the copy constructor must be simple and not user-defined. The technical term used in the C++ standard is that the copy constructor must be trivial. This means it must be implemented by the compiler, not have member variables which require allocation, and a few other rules. These restrictions on T mean, for example, you cannot store an std unique pointer inside an atomic type, since std unique pointer is not copyable. This error will be detected at compile time.
The key reason atomics were added to C++ is to prevent race conditions. As a reminder, a race condition occurs when there are multiple threads accessing a shared variable at the same time, and at least one thread is writing a new value. Picture one thread reading and another thread writing, and it is a race to see who gets there first. There is no formal definition in the standard for thread safety. The common interpretation is that all code which works with shared data produce a consistent result. In order for a program to be thread safe, it must not only be free of race conditions, it must also produce the correct result. Using atomics does not magically make your code thread safe. Data races may not occur, but you are still responsible for ensuring the algorithm works correctly, no matter what order the threads are executed. Given our main example of thread B reading values of 0, 10, or 20, the result is obviously unpredictable, but this is not considered a race condition. Using an atomic variable does not determine which value you will see. It simply guarantees the value will be one of the values previously saved. The terminology the standard uses to define atomics is rather interesting. Typically, we refer to the functions of a class as methods. For std atomic, these methods are referred to as atomic operations, which is unusual, however, it does not affect the functionality. There are a lot of atomic operations, and exactly which ones are available will vary depending on the T. The operations can be grouped into 4 categories, as shown in blue. The first 2 are the store and load operations. As the name implies, the store operation stores a new value in the atomic, which replaces the prior value. The load operation retrieves the current value from the atomic. The exchange operation stores a new value and returns what had been in the atomic as one single process. It is typically used to swap the value of some local variable with the atomic value. The compare and exchange operation is a bit more complicated. You must pass both an expected value and a new value. If the atomic matches the expected value, then the new value is stored in the atomic and the operation returns true. If the atomic does not match the expected value, the compare and exchange returns false and the variable expected is updated.
These are some examples showing the basic atomic operations. As we mentioned, it is always a good idea to initialize your atomics, even if you are using C++20. In this code, we are initializing the variable count to 0. On the next line, 5 is stored in the atomic. The std atomic class has overloaded assignment operators, so this line could have been written as count equals 5. We recommend always using the explicit store method to ensure the reader knows the variable is an atomic. Next, we retrieve the existing count by calling load. Again, this could have been written as a simple assignment. For the exchange code, the value of 10 will be stored in the atomic, and the variable data2 is assigned the old value of the atomic, which will be 5. The last line is showing a compare and exchange operation. If the current value in the atomic is 10, this succeeds. The atomic is set to 20, and result is true. If count is not currently 10, result will be false and the atomic will not be updated. There is the often overlooked side effect that occurs when this operation fails. The variable expected will be modified by the operation to reflect the current atomic value. In the case of result being false, you will typically see code which then examines the value of expected and takes some action based on that new value. This explains why the first parameter for compare and exchange cannot be passed directly and must be a named variable. Also keep in mind, expected could not be declared as const since it might be updated. Saying this precisely, compare and exchange receives its first parameter as an L-value reference. As we discussed in our C++ memory model video, there are several reasons your source code may not be executed in the order you wanted. In multi-threaded applications, this can have significant consequences and requires more work by the developer to balance correctness, practicality, and speed. The rules of memory ordering were added to the standard for performance reasons. The default memory ordering for atomics is the most strict option, and it is referred to as sequential consistency. There is a performance cost to this level of memory ordering, since it limits the ability of the compiler and the hardware to take advantage of certain optimizations. Fortunately, the C++ standard provides a way to relax these rules when your code does not require such strict control. Making use of these relaxed orderings can increase performance significantly. However, it is your responsibility to ensure the code can tolerate the potential reordering, which will likely occur. There are 5 main types of memory ordering defined by the standard. If you do not specify anything, your code will use the default ordering, which is the strict sequential consistency mode. This means all atomic reads and writes done by a given thread will occur in the same order as they appear in the source code. To override the default memory ordering, simply specify which one to use by passing a parameter to the atomic operation. The acquire and release ordering is a parameter which is only relevant or allowed for the exchange and compare exchange operations. Let's hold for a minute on this one and talk about the next two. The release mode can only be used for an atomic store. It prevents all reads and writes of non-atomic data from being moved to a position after the current atomic store. The acquire mode can only be used for an atomic load. It prevents all reads and writes of non-atomic data from being moved before the current atomic operation. The release and acquire modes are typically used when a thread is passing data to another thread. A typical example is where one thread does a store with release mode, and the receiving thread does a load with the acquire mode. This guarantees the data is available when the receiving thread reads it. Going back to the actual acquire and release mode, this is a combination of the other two modes. You would use this mode to simultaneously load the current value in acquire mode and store a new value in the atomic using release mode. The relaxed memory ordering places very few constraints on how the surrounding code is reordered, which gives the widest opportunity to the compiler for optimization. This particular mode sounds great for performance, however it should be used with caution. Typically you added an atomic to the code to protect access to some shared data, and although you are ensuring against race conditions, the compiler can now mix up how the code is evaluated. There is one other memory ordering called consume, but it is rarely used and the standard actually says it should be avoided. The Standards Committee is considering how to revise this ordering to make it actually useful.
Here is a simple example which may help to demonstrate how memory orderings are used in actual code. The atomic int is initialized to 0 in the main thread. Thread A will store the values 10, 20, and 30 using the sequential consistency or strict ordering. At the same time, thread B will load count using sequential consistency. To reason about the code for correctness, we want to consider the possible values thread B might see on lines 5 and 6. It is likely that thread B will read the same value both times, for example, 10 and then 10 again. It is also possible thread B will read two different values, perhaps 0 and then 20. It is important to explain that it is actually impossible for thread B to read values out of order. If the first read returns 20, then the second read must either return 20 or 30. Since sequential consistency is the default, the parameter we have in these examples could have been omitted from the store and the load operations. One of the most common ways memory ordering appears in multi-threaded code consists of a store using release mode and a load using the acquire mode. With these modes, the compiler and hardware now has more freedom to reorder other non-atomic reads and writes. In thread A, optimizations can happen before each store, and in thread B, optimizations can happen after each load. In this last example, we have switched to the relaxed memory ordering for all operations. Now the compiler is free to reorder any of these stores and loads, as well as reordering any non-atomic reads and writes. This means the two loads in thread B may see values for count in an order you may not expect. It is perfectly legitimate to have the first load in thread B return 30 and the second load return 10. It is also possible for another thread C to disagree, and it might do the same two loads and see 10 and then 30. This is a surprising result, even for some experienced multi-threaded programmers. Now that we have talked about atomics, it would be interesting to talk about when to use a mutex. We look forward to presenting this as the next part of the series.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.